Two loci, C1 and C2, defined as shown, where D is a real number. Find in terms of D the complex number which is represented on an Argand diagram by the point of intersection at C1 and C2, assuming that there is one. I'm just going to go straight into this. You need to know your three different loci. Okay, one of them that's not here is if you have the modulus of z or something like that equal to 4, then you get a circle with radius 4, in this case centered at the origin. The second one, which is what C1 is that you essentially have two circles and you can vary the radius and you end up getting the perpendicular bisector between the two centers. So for modulus of z, the center is just the origin, 0. And then for z minus 4d squared minus 36, the center would be at 4d squared plus 36. Like a transformation, I'm replacing x by x minus 4d squared minus 36. So actually a translation from 0 by 4d squared plus 36 in the x direction, or in the real direction. And like I was saying, you're going to get like some circles here, and it's where they intersect, and it's going to end up, as you draw different circles, I'm not going to demonstrate it here, but you will necessarily get the perpendicular bisector. You can also show it algebraically. Okay, so it's going to go there. And this, although there's a d involved, it's fairly nice because they're both along the real axis. And I'm going to get for C1 that x is equal to 2d squared plus 18 because I've taken the midpoint. Okay, I've just taken the halfway from 0 to 4d squared plus 36. Great, so that is C1. Now we've got C2. Okay, there's a couple of ways to do this one. It's going to originate at 12d, comma 3. So I'll just put it here. Okay, this is not drawn to scale. In this case, because I've got pi over 4, that's actually 45 degrees. I can draw it straight away, just as it's like the gradient's going to be 1. I've just remembered actually we should use an open circle because it doesn't actually have a value at that point in particular because you get arg of 0. It's good to get into the habit of doing that. Right, and then it's going to look like this. So two ways to derive this. Because we know that this is now 45 degrees, I can see that the gradient is going to be 1. So y must equal x plus c. Although let me just specify that x has to be greater than 12d. Okay, that is what that point is there, 12d and 3. I can, however, substitute that coordinate in to help me work out the intercept, even though it doesn't exist at that point. So I will write down that 3 is equal to 12d plus c. Therefore, c is equal to 3 minus 12d. And we've got our line, y equals x plus 3 minus 12d. Okay, I'm actually going to put boxes around these because they're so important. Now, before I do the next bit, I'm just going to very quickly derive it in a different way. This is particularly useful if the angle's not quite so nice. So we've got a complex number. This is y, this is x. I've got my arguments here. I can say that the argument of z is equal to, or tan of the argument of z is equal to y over x. Now for my complex number, I had z minus 12d minus 3i. That becomes x minus 12d plus y minus 3i. That's my actual complex number that I'm dealing with. So for me, it becomes tan of the argument, which was pi over 4, equal to y minus 3 over x minus 12. So you can also get the equation this way. And don't even worry if it's not in the first quadrant, it will still work out. Tan pi over 4 is 1, so I'll get y, I've just realized I made a mistake, that should have been 12d. I'll get y minus 3 equal to x minus 12d. and I'll add the 3 on and I'll get the same answer here. Okay, so two different ways. Probably the first way in this case was a little bit easier to understand, but the one in purple, don't neglect it, because if you had tan of pi over 6, for example, you get you get a half in that case, but you could get a third and things like that. So just be aware of it. We're actually nearly finished. So we're looking for where the two lines cross, and they've got to cross when x is equal to 2d squared plus 18. So y is just going to be 2d squared plus 18. Then I'm going to add 3 and minus 12d. And therefore the complex number that I want is going to be z equals 2d squared plus 18 plus the imaginary component 2d squared minus 12d plus 21. I, don't forget about the I. So just to recap, we've sketched the perpendicular bisector between 0 and 4d squared plus 36, because that defines C1, written down the equation of the line. We've sketched the arguments carefully, seen that there's this point of intersection here, written down the equation that relates to that, valid for x being greater than 12d. We could still use the point to sub in or use a more general idea. We've got our two equations. I mean, they're kind of simultaneous equations, but we already have the value of x where they intersect, so just sub it in to get the value of y, and then just make sure we write that back as a complex number. Finally, explain why the solution found in part A is not valid when d is equal to 3. So when d, do you know what? I'm just going to bring the question down. There's just too much writing here. Yeah, you could think about the graph, what happens to the graph when d is equal to 3. Or you could think about the equation. But when d is equal to 3, we're going to get x is equal to 2 times 9, that's 18, plus 18, I'm going to get x is equal to 36. And then 12d is also going to be 36. So actually, I quite like it from the diagram. What this means is the line is actually going to start here. And that's where the problem lies. So when d is equal to 3, the loci C2 is only valid for x greater than 36. And this is, as I said before, like you get the argument of 0 when it's 36, and that is not allowed. So that means arguments of z, then it's minus 36 cannot intersect x equals 36. Solution from A not valid. Okay, I think that's enough. It's just basically explaining why there's the problem right here. All right, well done on your efforts on this question. Hope it all makes sense now. Keep going.